All right. Now we've talked about how the conjugate base of an acid, right, might be a strong base if the acid is a strong acid. Does that make sense?
Kind of. Can you write that down a little bit?
So, for example, I have a strong acid. I think I said that right. Maybe I said that wrong. Strong acid, H plus, Cl minus. That conjugate base is going to be very weak. It's not going to take that proton back, right? I mean, we don't even draw a reversible arrow on a strong acid. Weak acid, H3PO4, right? H plus, what's the resulting conjugate base for phosphoric acid?
H2PO4 minus.
Very good, H2PO4 minus. Not the strongest of acids, therefore, this H2PO4 minus, and this is phosphoric acid is a weak acid, therefore H2PO4 minus is a conjugate base of significant magnitude, right, in terms of its strength. For sure, if I had HPO4 2 minus, and I release that hydrogen ion and form PO4 3 minus, this would be a very strong base. This is not a very weak acid, or not a very strong acid, but its conjugate, therefore its conjugate base is going to be a pretty strong base. All right? Another way that you can get the phosphate ion all by itself and behave like a strong base is to add to solution something like sodium phosphate, Na3PO4. Because that is an ionic compound that's completely soluble, you're going to release 3 sodium ions and a phosphate ion. And when you release that phosphate ion, PO4 3 minus, it behaves like a strong base. It interacts with water, and it grabs those hydrogen ions, HPO4 minus, and creates hydroxide ions, or HPO4 2 minus, and creates hydroxide ions. Additionally, some of these HPO4 2 minuses are going to take another hydrogen away from a different water molecule and form another hydroxide ion and some H2PO4 minus. And that is also going to do the same thing for some water molecules. All of those will be in equilibrium. So the result is every time a proton is taken away from water, you get hydroxide ions. So sodium phosphate, because phosphate is the conjugate base of a weak acid, it makes it a relatively strong base. And you can get it simply by adding sodium phosphate to solutions. Okay, so which statement about acid strength is false? Binary acids get stronger as the anion gets larger. What do you think? Is that true?
Binary, that's like HCl, HBr, and HI, right? That's true. As HBr, you go down the periodic table, and the acids get stronger for binary acids.
Very good. Oxoacids get stronger as the central atom increases in size.
Increases in size. Oxoacids get stronger as central atom increases in size. Let's see. HClO4 is a strong acid, and it's an oxyacid. HBrO4 is not a strong acid, right?
Okay, yeah, we don't even talk about HBrO4, but that's right. That's a good example. So that's not true. Oxoacids don't get stronger as the central atom increases in size. Let's see. Oxoacids' strength increases with increasing oxidation state.
Oxoacids' strength increases with increased oxidation state. So let's look at oxidation state. I don't know necessarily right off the top of my head. phosphate, or phosphate and phosphite.
All right, so if we go for H3PO3 and H3PO4, what's the oxidation state of this phosphorus here?
Okay, so oxygen is -2, 6 of them -6, hydrogen +3. So +3 plus whatever the phosphorus is, -6 equals 0.
Yeah, so here the phosphorus is a +3, is that right?
Okay. And then over to the right there, -2, -8, +3. It's a +5 there.
Okay, so this is a +5. Oxoacid's strength increase with increasing oxidation state.
Yeah, that's true. That's true.
Very good, that's true. We see that that's true. We see that H3PO4 is a stronger acid than H3PO3. We talk about it in terms of the number of oxygens, and that's essentially how you're going to relate oxidation state. More oxygens, higher oxidation state. Okay, so which compound or which statement is false?
The B. B is false.
All right, very good. Good job. All right. Bronsted acid bases are the typical way to kind of talk about acids and bases. However, we want to have a second way, which is called Lewis acids and bases. Lewis acids and bases behave very similar in some ways, but we can talk about acids, Lewis acids and bases, even when they're not typical Lewis or not typical Bronsted acids or bases. So, for example, this is an example of a Lewis acid-base reaction here, but no hydrogens are actually moving. All that's moving is a pair of electrons. All right? So this is different because usually with a Bronsted acid, we can just think about our hydrogens coming on or coming off. But for Lewis acids and bases, we can't just follow the hydrogen because hydrogens aren't moving always in Lewis acids and bases. There is one Lewis acid-base reaction that is very easy to think about and that has hydrogens moving, and that is when we take NH3 and react it with H plus to form NH4 plus. Now, NH3 is not an acid. It's a base. H plus is an acid. And when this reaction occurs, H plus is behaving as the acid, this ammonia is behaving as the base. And the way it occurs is these electrons reach out and grab that hydrogen. Again, this is the acid, hydrogen ion, this is the base, ammonia, okay? And so this is an example of a Lewis acid-base reaction. And so when we can use this as our example of a Lewis acid-base reaction, then we can look at a different Lewis acid-base reaction and see the pattern. So in a Lewis acid-base reaction, there's a little couplet that we remember. A Lewis acid accepts a pair in an electron share. A Lewis acid accepts the share in an electron pair. And you see that here. The electrons are reaching out and grabbing on to the acid. That means that in this system here, BH3 is the Lewis acid because Lewis acids, accept the share in an electron pair. All right? The Lewis base donates the pair in electrons in an electron pair when you have a Lewis acid-base reaction. So, Lewis acids are base. And neutralization is the formation of a covalent compound between two molecules. Okay, let's see here. Here's our standard model. Which one of these is the Lewis acid in this model?
The H plus was.
That's right, the H plus is. And the electron density comes off of the lone pair here and grabs onto that hydrogen to form a new molecule. How about this one here? Where is our Lewis acid in between these?
What's happening there?
Okay, good question. So you see this thing with its lone pairs, and you see this boron trifluoride, and then we create boron tetrafluoride ion. So what's going on here?
It looks like the electrons are going from the F minus to the BF3?
That's right. Electrons are coming off of here onto there and forming another bond. So what does that mean? Who is the acid and who is the base?
Well, the arrow is coming away from the fluoride ion, and the boron is accepting the share. So the BF3 is the acid?
That's right. Very good. So just like the electrons were coming from the base to the acid, here the electrons are coming from the base to the acid. Okay, good job.